Finite element analysis of hydraulic actuator by using CAE tools. Abstract: a hydraulic system is a fluid power system that is commonly used in industries due to its ability to sustain high pressure. So, here in this paper, double-acting hydraulic actuator is designed based on the force acting on it, and the stroke length. Analysis of different parts of actuators is done by using CAE tools, checking for the equivalent stresses and deformation. Two different materials are also used to check proper material to be used. Keywords: hydraulic actuator double-acting analysis. Introduction. Hydraulic actuators are the end results of Pascal's law. Hydraulic actuator is the device which converts hydraulic energy into mechanical energy. It consists of cylinder that transforms the flow of pressurized fluid into a push or pull of piston rod. In double-acting actuators, the fluid pressure can be exerted from both sides. Hydraulic actuators are rugged and suited for high-force applications. Methodology. The load of 21,832 N is to be sustained by actuator, but if fails suddenly, so taking into account sudden loading conditions, it should be designed for 43,664 N, 21,832*2. So by using Kasha V5 models are made, and every component is analyzed separately using two different materials that are low-carbon steel and E335 steel. Low-carbon steel is used as it is lighter in weight with good yield strength, tensile strength, corrosion resistance, ductility, whereas E335 steel is practically used in industries as a material. So here we find out which one is better. Design procedure. The following assumptions were taken into the consideration of the design of the cylinder, piston rod, and seals in the hydraulic cylinder. Working fluid is mineral oil. Available pressured Pa equals 200 bar equals 200*105 Pa. Atmospheric pressure equals 1.0135*105 Pa. Stroke length equals 1135 mm equals 1.135 m. Cylinder output force equals 43664 N. Factor of safety equals 3. End fixing factor equals K equals 0.7. Properties of materials used. Table 1. Material. Low carbon steel. E355 steel. Ultimate tensile stress 430 MPa. 540-620 MPa. Yield tensile stress 215 MPa. 290-450 MPa. Young modulus, E. 210 GPa. 190 GPa. Design of piston rod. The rod is more likely to fail by buckling under the compressive load. In this case, the rod behaves like a column and is subjected to buckling. Therefore, Euler's formula in the equation below for long column can be used to obtain the piston rod diameter. P equals 2EI/L2K2. Where P equals buckling load, N, L equals the column length, M. I equals moment of inertia, M4. E equals Young's modulus of elasticity for the column material, Pa. K equals the end fixing factor equals 0.7. E equals Young's modulus of the material used in this design calculation is 120 GPa. P equals cylinder force * factor of safety equals 43,664 *3 equals 130992 N. 130,992 equals 2210-109 I, / 1.1352 0.72, I equals 39.894 *10-9 M4. D4/4 equals 39.894 10-9. D equals 15 mm. From BAME Hydraulics Corporation Catalog of Metric Rod Wipers and Piston Seals, the nearest standard rod seal diameter is 20 mm. Design of the piston. Let A be the full area of the piston and A be the cross-sectional area of the piston rod. Since the design is a double-acting double-ended hydraulic cylinder, pressure is X on both sides of the rod, hence the area which the pressure is acting on is given by AA. The force produced is given in the equation below. From BAME Hydraulics Corporation Catalog of Metric Rod Wipers and Piston Seals, the nearest standard rod seal diameter is 100 mm. The bursting stress can be referred to as the amounts of hoop stress and longitudinal, axial, stress that are produced in the wall of the cylinder when subjected to internal and external pressures that may cause the material which the cylinder is made from to fail. This happens if the hoop stress exceeds the tensile strength of the material. 222. 222. The hoop stress, H, of a cylinder can be determined from the Barlow formula as shown in the equation below. H equals P, do 2 plus D, slash, do D, where P equals oil pressure, 200 bar equals 200 *105 pa do equals outer diameter of cylinder equals 55 mm d equals inner diameter of cylinder equals 200 105, 1152 plus 1002, slash, 1152 plus 1002 equals 144.031 MPa. 2222. 2222. Also the longitudinal stress is given by L equals P1 R1 P2 R2, slash, R1 R2. Where P1 equals internal pressure, 200 *105 pa. P2 equals external pressure, atmospheric pressure equals 1.0135. *105 pa. R1 equals internal radius R2 equals external radius. Equals 200 105. 5010-3, 2, 1.0135105, 57.510. 3, 2, slash, 57.510-3, 2, 5010-3, 2. Equals 61.599 *106 MPa. Result and discussion. Rod. Cylinder. Piston. Stresses, MPa. 153.29. 179.4. 240.33. Total deformation, mm. 0.75084. 0.034873. 0.10226. E355 steel. Rod. Cylinder. Piston. Stresses, MPa. 141.09. 181.45. 237.92. Total deformation, mm. 0.83055. 0.038654. 0.11319. Conclusion. Here, design and analysis of different parts of actuator I.E, piston rod, piston cylinder is done using CAE V5 and ANSI. From the above obtained value, we can conclude that the stresses developed in low-carbon steel are more than E355 steel and the total deformation of E355 is more than low-carbon steel. Hence from obtained data it is beneficial to use E355 steel.